I just saw that and thought I'd pass those thoughts along.
Sure.
So did you have a good weekend?
Not bad, not bad. How about yours?
Overall, it was not bad. The Panthers won, and I didn't get caught into race traffic for the Martinsville race because that track is only about 10, 15 minutes away from my house. So, yes, I do live that far away. Yes. But anyway, otherwise, pretty good weekend.
I know how that goes. I grew up in Bristol. And of course, we have horrible race traffic.
Yes, and just there's no good parking there. But, and they ruined that track when they reconfigured it. I am so sorry. Whether progressive banking or what, no, it's just they ruined it. But that's part of it. I don't watch NASCAR anymore.
Yeah, I don't either.
Because they ruin the fun ones. Oh, yeah, that's not, anyway. I've got my whole theory on the whole NASCAR thing, but Ranch Family, they're setting things up to try to get the temporary ticket ratings so they can sell out completely. And that's what all the gimmicks are with the stages and the chase and all that, whatever, just because the TV ratings are horribly down. Because they messed up by, doing the last TV deals with Fox and with NBC, so half of the races are not on broadcast. They're only on cable on these weird Fox Sports 1 or whatever channels that a bunch of people don't have. And, I actually looked years ago at the ratings for the races when they were on ESPN that everybody that's got cable gets was half of the ratings of the races that were on Fox, that kind of stuff. They're going to be even worse still for these other stations. And I think they messed up. Anyway, but enough about that. Let's talk about some plans, shall we?
Sounds good. So just wanted to let everybody know that I did get an email about the quizzes not showing up for people. So I'm going to try to work that out today right after class. And, of course, we have a lot of outstanding assignments that some people have not done. So we're putting solid deadline dates on those. And if you don't get them in by that time, then that's it. Get a 0. So look for those between now and Wednesday. We've got just 2 chapters left in this second unit. And we're going to cover one on water today, and then on Wednesday, hopefully get through mineral nutrition. That's going to give about a week kind of in between for us to really start on these crop projects. And I want to thank everybody that did finally get in there and sign up for their crops. So basically the way that's going to go is we're going to pair you up into teams, and you'll be delivering kind of an online presentation for your crop project, as well as doing kind of a written portion to turn in for yourself. Anyway, more details on that next week. And if everyone gets through all the quizzes, I think I'm going to have to probably make some of them shorter because it's going to be difficult to get all these quizzes in the allotted time. So we can do a little bit of review next week, and then following week have our test, and then a midterm after that. So lots of stuff going on. Again, let me know if you guys have any questions, comments, or concerns, gripes or grievances about anything. Let's talk a little bit about water in plants this morning. And again, some of this stuff we've already touched on, so a little bit of it will be review, and probably some of you have read up and researched on some of this stuff yourselves. So first, as you may have known, water makes up most of the plant's mass. We're saying about 90% of most plants. That's not every case. There's some cases where there's a lot more biomass, a lot more dry matter in particular plants. But for the general plant world, usually about 90% of tissues is made up of water. which is kind of fascinating because it means that when we're selling produce or selling whatever product we get from our crops and we're shipping it, we're really just shipping kind of packets of water in a way. Of course, water is a limiting factor for plant growth because of that, because it makes up most of the tissues. And especially in arid areas. Of course, in our area, we often don't have to supply irrigation water. It can help. It's really interesting, though, to me, in my experience, to watch the difference in natural rainfall versus irrigation. And it's like you seem to get so much more growth from natural rainfall, at least when it's substantial. So, of course, water is required for many processes of the plant, including seed germination. As we know, you have to have moisture in order to get seeds to germinate. It also serves as part of the plant's structure itself, making up the cytoplasm, as well as many of the parts of these processes in the plant, parts of proteins. It's the hydrogen and hydrogen and oxygen atoms that really make up a lot of these materials, as we discussed in this unit. It's also important for carrying minerals into and through the plant, and for transporting all these other metabolites in plants, parts of the metabolic processes from photosynthates and other biochemicals. Finally, water also cools the plants, and they put evaporation on here. That does cool plants, but it's more transpiration that really cools the leaves of plants. If we don't have water, then plants don't grow. And if we continue to go without water, the plants die. And almost all of that water that plants get comes from the soil, through the roots. There is a small amount that is able to be taken in through leaves, but mostly it's coming from the roots. Talk about some characteristics and properties of H2O and what really makes it so important for life on Earth. First, water is known as the universal solvent. We use it to dissolve more substances than any other liquid, and it's because of its unique properties that it's able to do that. It is one of nature's most stable compounds, and for a long time it was really actually considered a single element and not a molecular compound. And as you all know, it's made up of 2 hydrogen atoms attached to 1 oxygen atom, H2O. And here's just an image depicting that kind of molecular structure and the angle at which these bonds are located. The polarity of the molecule actually creates a really interesting, you don't really see the same angle in any other substance. And because of that, it gives all these characteristics and properties that makes it so important for life on Earth. So as you kind of see here in the green, these are the shared electrons, which allows it to basically create this really strong bond between the hydrogen and oxygen atoms. So they call this this lack of symmetry here a dipole because of the polarity of the hydrogen atoms being held to the oxygen atom. We have more positive electrical charge, and on the opposite end, a more negative charge, which allows them, one, for water molecules to bond together, but then also allows them to bond to other substances. Bonding together of hydrogen to oxygen creates this physical property known as surface tension. And it's because of this molecular attraction between the water molecules that we get this basically film on top of water that results in this really strong ability for water to, it almost seems like a solid. For instance, if you drop something into water from a height, when it impacts the water, it has to break through that surface film, and there's a lot of energy that is required to do that. Therefore, if you guys have done a belly flop, you get a lot of surface tension. Surface area combining with that surface tension, it hurts, right? It's like hitting more of a solid substance in a way. So even in its liquid state, it can almost act kind of like a solid because of the water film. Sorry if anyone's afraid of spiders, but this is an interesting animal that is able to exploit that surface tension. This is the fishing spider. And as you can see in the image on the right, it's able to basically distribute its weight along that water film. And even though it's a large insect, or arachnid, I should say, it's able to actually kind of glide on the top of water. And when it does actually fish, when it actually catches its prey, it will contract and basically bring all of its legs together so it breaks through that water film and can grab a little fish. So surface tension is a very fascinating property of water that results from the hydrogen bonds that really creates energy in the water, as well standing water, as well as water in the soil, as we'll talk about here in a moment. Water is also very interesting in its different phases. Of course, in the liquid state of water, the attraction of the water molecules is somewhat random. But as it freezes, you get like a really symmetrical, rigid lattice kind of formation of these bonds of water molecules to other water molecules. And then it has kind of an open, porous structure as well. It also, water, because of this, because of its unique bonding and polarity, has an unusually high specific heat, which means that it can act as thermal mass. It can store a lot of heat and kind of in the water, but doesn't necessarily increase the temperature of the water that much. Which is why we get things like steam or kind of fog coming off of waterways this time of year. I mean, why my animations are doing that. So here's a little bit more about water phases. It's one of the very few molecules out there that can exist in all three states, as a solid in the form of ice, or liquid as we usually know it, or as a gas, as water vapor or steam. And you can, sorry, this image is kind of blurry, but you can see here that the structure, the molecular structure changes. So as it forms into a solid, we have very tight and symmetrical bonds in the water molecules. And liquid water, the molecules are kind of sort of floating around, as well as anything else that is dissolved into that solvent. And then in gas, the molecules are moving very quickly, and they're dispersed throughout that state. So these different water phases can, of course, also occur in the soil too, based on temperature and different molecular forces. Strongest in ice, weakest in gas, lowest temperature in ice, highest temperature in gas state. So water held and moving within the soil, what we call the soil solution, because it's not just water at that point, it's also these dissolved mineral nutrients, and sometimes also more dissolved oxygen, as well as the water itself. And this can move through the soil pore spaces in both liquid and gas states. When all the pore spaces in the soil are filled with water, then they're known to be saturated. If they are not filled with water, if they're just all filled with air, then it becomes kind of the opposite of saturation. It's unsaturated, and both of these can be bad for plants. If plant roots remain inundated, kind of in a saturated soil, then the oxygen that should be in those pore spaces is missing, and plants cannot uptake water. So we can actually get wilt both in saturated and in unsaturated soils. Of course, when the pore spaces are mostly air, the soil is too dry for good plant growth. And all of this is going to vary with the soil's texture and structure, and more on that in just a few minutes. The ability of the soil to retain water is called, guess what? It's water holding capacity. Pretty simple, right? So this is kind of how water travels through different soil textures. On the left, you got kind of a depiction of a sandy soil. On the right, you've got a clay soil. So, of course, water quickly moves through the gradient in a sandy soil. All of the pore spaces in soil actually have to be filled with water in order for that front to move. You can see this wetting front pictured over here on the clay side. It often kind of has this kind of teardrop or raindrop sort of shape. And basically that's just the water passing through these different pore spaces from wet to dry. Of course, water follows the path of least resistance. So it's the number and the size of these soil particles and the texture as well as their structure kind of combined that allows water to move through the soil at different rates. And as you might imagine, clay soils, and I guess this is review, hold more water longer. Silty, less, sandy, even less. So ideally, we want to get kind of a good combination of clay, silt, and sand particles in our soil structure so that we have some areas that hold water and some areas that freely drain it. There are three forces that are responsible for water actually moving within a soil. First is gravity. And of course, that's the chief force that causes that wetting front to advance. It's the downward movement of water by the pull of gravity. Then we have adhesion and cohesion. And adhesion is just the force of the attraction between unlike molecules. And usually what we see is soil particles and water. And really what we have going on here, if we think back to that presentation on soil, the soil particles themselves also have charges on them, that often cations or anions. And remember, we look at that cation exchange capacity as the ability for a soil to hold on to these positively charged ions. In adhesion, basically we're having these positively charged ions held to the soil particle that then bond to water molecules, or just the positive charge of the particle itself bonding to the molecule. I think of adhesion sort of like a magnet. There's some force, and in this case it's not really electromagnetic, but it's kind of it is electro in a way. It's electron bonding that causes that adhesion being tightly held to the particles of the soil. Cohesion is really just like molecules being attracted to each other. So cohesion is really, we look at as water being bonded to water. And adhesion and cohesion combine in the soil to allow water to actually move in any direction. It can move upwards on a gradient, it can move downwards, or it can also move side to side, kind of laterally, as a result of the additive forces of adhesion, the water bonding to the solid soil particles, and cohesion, where the water is bonded to itself. And this combination creates what we call capillarity, or capillary action in soil, where it's not just moving down with gravity, but it can be moving in any direction. And that does include up. So water with these forces can overcome the force of gravity, which is really fascinating to see, and part of May the miracle of life on Earth. So this just illustrates capillary rise through different diameter tubes. Basically, as soil dries, the water surrounding each soil particle then thins, the water film, which then allows that water to move in any direction. These combined forces of adhesion and cohesion allow this attraction to really rapidly increase, and then that in turn makes it more difficult for the plant to actually extract water from the tightly held soil particles. So it's kind of a little bit counterintuitive how this works, and we'll try to break it down to where it makes a lot of sense. So the forces actually can be measured in terms of their energy, and we look at that as water potential. It's really, just as it sounds, it's the potential for water to move. And we use this Greek letter psi as kind of the mark for water potential. This determines the direction that water flows, and as we mentioned earlier, water, of course, naturally going to flow on the path of least resistance, from high to low water potential. We measure it in these units of pressure. Most commonly today, we use atmospheres or megapascals as the units of pressure that we measure this water potential. So when we have saturated soil, meaning again that basically all of the pore spaces in a soil are filled with water, we say that the atmosphere has 100% relative humidity, so also the air also is full of water. At that point, there is zero water potential, which causes it basically just to be pulled away by gravity. And as the water drains away, the soil water potential decreases. It becomes more negative. So we're starting at zero and we're going down. This negative potential basically creates the need for the plants to pull the water away from it. And it's not really the plants necessarily that are doing that. It's more just the movement of the water towards the roots, and then the roots sort of intercept the water in the soil. They're kind of moving, the roots are moving towards the water in the soil, kind of searching for it, but the water is also moving towards the roots. Basically, when the negative potential gets to the point to where it's greater than the gravitational pull, then water stops draining. So we can look at soil water potential based on these factors. First, gravity, only really working when the soil is saturated. Matrix potential is the resulting potential from adhesion and cohesion, again, between the soil particles and then water bonding to itself. And then we have this osmotic flow, which is caused by dissolved salts in the soil water. And this is different than osmotic movement in plants. In soil, it's only caused by salts. You have to have salts. And the main way that we get salts in soils are either through irrigation, fertilization, or it does happen naturally in really arid areas too. So when we irrigate, we're moving water down through the profile of the soil by gravity, but then it can move upward and laterally by the matrix potential, again resulting from the adhesion and cohesion between the soil particles and then water molecules to each other. So what happens when we get water, and you can kind of see it sort of starting in this image here. You see it sort of forms this like teardrop rounded shape, as it moves, again, both laterally, in some ways upward too, and then down by gravity. So it's the wetting front is not just straight down like you would expect. If you were to dig like a soil pit beside of an irrigation canal or beside even just like a drip emitter, you would see this wetting front with this kind of teardrop shape, moving in multiple directions, not just down. So this is just a depiction of what salts can do in water itself. So they've done this illustration of a plant inside of a beaker with water that has salt in it, and then one that just has pure water. So if the salts are present in the soil water, then it can create this osmotic energy. And if that is large enough, it will prevent water to move into the plant itself. And then you'll get wilt. So too much salts are a bad thing. And of course, our fertilizers are mostly, not all fertilizers, of course. If you're using manure, for instance, it's not this same deal, but basically all of our synthetic fertilizers are bonded to salts, which makes them more water soluble. But if you have accumulation of these fertilizers, and especially in specific horizons, then it can inhibit water uptake because of basically it's creating this osmotic water potential that makes it more difficult for the plants to actually obtain water from the solution. We can get this especially when we've used fertilizer for long periods of times without a sufficient, kind of flushing of these salts out of the soil. So the nutrients move, but the salts often can remain. So really, the areas that we get this most often are in arid climates. It's super dry, and in these super dry areas, we don't have enough natural rainfall that causes actual full soil saturation that can remove the salts. Salts are, with the osmotic potential, are often actually brought up further, up into the A horizon of soil often. And that's why they generally tend to accumulate. And we have to have natural rainfall without included salts in order to actually flush fertilizer salts out of the soil solution eventually. So you'll see that happening, especially in arid climates. Or if you're, doing some greenhouse production or, even just indoor plant production, you have to flush the salts out of the soil at some point. So what often happens as a result is you get this kind of fertilizer burn. If we go back to this picture, you can kind of see that happening in the leaves here. That's actually a good way to know if it's more salts or if it's more just lack of water. You'll start to see basically it looks like yellowing or more often kind of orange or brown tissues on the margins of the leaves. You can also get fertilizer burn though, just from having fertilizers contact the leaves themselves. And it's basically the same deal. It's the salt is attracting the water out of the leaves, causing this kind of burn-like look. All right, so here we have basically, what's going on in the soil. So we have water being infiltrated into the soil, and it basically travels through and fills up the pore spaces. And in A there, we have a saturated soil. Water has filled up all of those pore spaces. Looks like they have a few that are empty, but technically water would fill those as well. Maybe they're meaning for that to be a soil particle, but in this case, basically the water potential is close to zero in terms of pressure. And however, at this point, water is not really available to plants because it's being naturally drained by gravity. In B here, we have soil draining, and then you get a better air to water ratio. And you can see these soil pores basically opening up a little bit more. We have to have both air and water in order for plants to actually be able to uptake water. So B, this is kind of pictured as field capacity. And basically field capacity is when the gravitational forces end and then water actually becomes available to uptake by the plants. And they note here that that's at about 0.33 atmospheres. That should actually be negative 0.33. If the soil continues to dry, then the water film becomes so thin that extracting the water requires greater tension, greater energy, in this case 15 atmospheres, to overcome that negative energy. So it would actually be like negative 15 is the water potential in C. So they would have to have 15 to overcome that and actually be able to uptake water. And that's more than most plants are able to actually use. And at that point, if they continually stay in this state and are not able to eventually get water, then it will permanently wilt and eventually die. This is going to be different for different soil particles, different textures, and different structures. Many different things affect this. So that's why it's really important to test your soil, look at your soil structure, and also to look at the bulk density. You know, density of your soil tends to increase as you have things like compaction, for instance. When you have compaction, then you're decreasing the air spaces in the soil. And it makes it more difficult for water to infiltrate and to drain and also to be uptaken by plants. So here's just another image here kind of showing, adding kind of in the pressure here in terms of atmospheres. So again, soil texture determines the relationship between the soil water content and the soil moisture tension, which again, the plants have to overcome that tension in order to be able to uptake water. Soil water content at which a plant wilts and cannot recover is known as the permanent wilting point. So at that point, there's nothing you can do if you reach the permanent wilting point. However, there is also the temporary wilting point too. And I know this is not the best drawing, but again, it kind of shows how at saturation for a long period of time, a plant will die because it's basically being starved by too much water. You have to have a little bit of air in there for the plant to be able to uptake the water. This smothers the roots and basically causes plants to wilt, although that wilt might look a little bit different. The best way to really see whether wilting is occurring from too dry or too moist of water is just to feel the soil itself around in that rhizosphere. In this case, kind of in the middle where we have saturation and gravitational water is still draining it off. You can have too much water, you can still have temporary wilting, and you can also have healthy looking plants, but also still using more water than needs to be used. Of course, in natural conditions, we can't really control that. Notice we got field capacity right here in the middle. And in between field capacity, again, where water has basically all the gravitational water is drained off and all that is left is what is the adhesion and cohesion water. At that point, we have plant available water between field capacity and the permanent wilting point. So here we've got a temporary wilting point of water. The plant can recover if sufficient water is given back. The permanent wilting point is where basically there's too much energy holding. There can be water in the soil here, but there's too much of a negative water potential. Mostly just adhesion water at that point, just water being held to the soil particles, and the plant roots are not able to overcome that energy, and then they wilt and they die. If the soil becomes air dry, which is basically really beyond the permanent wilting point, then all liquid water is completely gone, except what is held as a very thin, tightly bound layer around the soil particles, that adhesion water. And we call that adsorbed water, also known as hygroscopic water. At that point, again, there may be water in the soil, but the tension is just far beyond the availability for plants to be able to use it. So again, available water is the water that is between field capacity and saturation. Available water is between field capacity and the permanent wilting point. The water that is between saturation and field capacity is not considered available because it is continually lost through that gravitational drainage. So what happens, basically, we have the same kind of structure of plants in the roots as we have in the shoots. We have root xylem, and water is able to enter through these membranes into the root xylem by both active and passive forces, which allows upward movement of water into the shoots and then subsequently into the leaves and other plant parts. Once that water is actually in the xylem, the potential or tension decreases from the root to the stem to the leaves, and then finally through the leaves to the stomata and into the air. And this is really what causes there to be turgidity in plants, this constant movement of water through the plant. We also have minerals that are dissolved in the water, plant nutrients basically, carried to the leaves, stems, and fruits via that xylem stream. And again, we've got decreasing water potential from the soil through the plant to the atmosphere, creating this tension that pulls this cohesive chain of water molecules first from the soil into the roots, and then through the xylem of the stem and leaves, and then out into the atmosphere. So notice the different potential here. It's more negative as you go up, which means there's more energy, and that creates the turgor pressure, the turgidity of the plant that holds it up. When you have lack of that pressure, that's when you get wilt. When we have that water flowing from the roots to the uppermost and then actually throughout the leaves, that's called the transpiration stream, which pulls water in the leaves and then out of the mesophyll cells and then through the stomata to the atmosphere and water vapor. So we have a water potential difference being created between dry mesophyll cells and the walls of adjacent moist cells. It's kind of like the same deal with a wetting front, except going through the plant, through cells. Also, this evaporation or transpiration of water from the leaves is one of the most important ways that a plant regulates its temperatures. Think about it just as, how we sweat to maintain our body temperatures. It's basically the same thing, except a little bit different in the mechanism anyway. So osmosis is a little bit different inside of the plant than it is in the soil solution. And in the soil, it's basically only created, we only see osmosis through the presence of salts. But in the plant, we have the flow or diffusion through basically semi-permeable membranes in the plant. that can move water throughout the plant. And it's kind of going through this gradient, basically, of different membranes until it's found its final resting place, pretty much. So there are basically differences in energy creating these flow conditions through the membranes, and then when there is no differences, when there's equilibrium, there's no more osmosis. Some of the water that is actually being transported is actually used and kind of utilized into plant structures, kind of separated from water itself to hydrogen-oxygen bonds into different chemicals, or it could be held in the cytoplasm. Some of it's being used in the biochemical processes, and then some of it is just stored in tissues in the cells of plants. And so it's the water volume in the cell that creates turgor pressure that gives turgidity to the plant, as well as kind of that gradient of that transpiration stream throughout the plant. Minerals, of course, are provided by the plant or by water to the plant, as well as used in the process of photosynthesis to create the carbohydrates and other chemicals in the leaves. So we kind of have both movements, transport of water molecules containing or being linked to other nutrients and minerals, both going from the leaves to other parts of the plant, as well as from the roots, from the soil into the plants and to other parts as well. So it's for a long time it was actually just thought to be one direction, but now we know that water moves in both directions, carrying nutrients in that water solution throughout the plant. And it's able to absorb these nutrients through a high concentration gradient by active transport, which is facilitated by special proteins in these plasma membranes. And we got that depicted here. A potassium ion basically being carried first through water to the roots. And basically what we're looking at here is just kind of this carrier protein that is able to come to the edge of the membrane and absorb that nutrient and then move it through this kind of membrane right here, the semi-permeable membrane, in this case known as the plasma lemma, and then it releases it into the cytoplasm, whether that's inside of a cell or to another membrane and to the xylem, transporting it upwards. So it is an energy requiring step for that protein to move and change shape so that it can actually absorb and move that potassium ion. So this is just kind of a simplified illustration of how nutrients are moved throughout cells. Sugars, on the other hand, move throughout the plant primarily in the phloem tissues. And if you remember, xylem is usually for water, and phloem is usually for food. However, water and nutrients can travel through either the xylem or the phloem. It's just that generally the phloem is taking sugars and moving them throughout the plants, down from the leaves to the roots, or utilized in other storage organs throughout the plants. When we have woody perennials, then the phloem tissue is basically just underneath the bark, and it is part of this production of secondary vascular tissue that is what really creates the ability to have a woody plant. So there's a few different ways by which these metabolites, the ions, and the water itself moves through the plants. First, we have diffusion, which transports ions and molecules very slowly, kind of in mass. We have cytoplasmic streaming, which transports these molecules and ions within the cytoplasm faster than diffusion. And then multi-directional mass flow, translocation of the material in the phloem itself. And finally, we've got very rapid upward movement of water and mineral nutrients throughout the xylem. So diffusion is kind of the slowest, and it's just transporting these from one cell to the other via a carrier. Cytoplasmic streaming isn't moving through the cytoplasm. Multi-directional mass flow is the materials when they're moving through the phloem, and then the quickest is the upward movement of water and the minerals inside of the solution through the xylem. And that's that for water. Anybody have any questions, comments, or concerns? All right, well, that's it for today. Again, check back. I'm going to try to figure out our quiz situation and make that available to everybody. I don't know if some of you are able to see it or if no one is able to see it, but we'll make sure that those quizzes are available today, as well as we'll be putting up some announcements about missing assignments. Probably give you guys one last chance to get those in, and putting the hard deadlines, especially on the lab assignments that some people have not done at all. So check back and kind of get that done so you're up to date. And we'll be looking at the last chapter of the unit on Wednesday.
Okay. Bye.
Have a great day.
You too.